In the class, we are going to identify the IR active vibration in a molecule, the IR active vibrations in a molecule. Okay. In the last class, we were dealing with the identifying the symmetry species corresponding to the vibrational modes in a molecule. And you already know that the molecules can undergo certain normal modes of vibrations, right? Certain normal modes of vibrations. But all these vibrations are not IR active. For example, if you are considering carbon dioxide, this is a linear molecule. Carbon dioxide is a linear molecule, and its dipole moment is zero, right? And when this carbon dioxide molecule is carrying out vibrations, what is going to happen to this what is going to happen to this dipole moment? That is what I am going to check now. Okay. For example, I am going to consider this type of a vibration. This is called a symmetric stretching. Means both oxygen atoms are going away from the carbon atoms simultaneously, and after that they will go to some extreme, then it will come back and they will come closer to carbon at after some time. Okay, so this is a vibration going away from the carbon simultaneously, coming closer to the carbon simultaneously. This is called the symmetric stretching vibration. Symmetric stretching vibration, okay, in carbon dioxide. And you can see that during this vibration, there is no dipole moment change. Actually, carbon oxygen bond length is changing continuously during this vibration. But whatever change is happening here in this side of the molecule, that will be cancelled. The effect of that will be cancelled by the change which is happening, simultaneous change happening here in the left hand side of this molecule. So at any point of vibration, if you are arresting the molecule and checking its dipole moment, there will be no difference from the dipole moment. No, there will be no difference in the dipole moment from the dipole moment which we saw in the equilibrium position. അല്ലേ? Equilibrium പൊസിഷനിലാണ് എന്തായിരുന്നു അതിൻ്റെ ഡൈപോൾ മൊമെന്റ്. അതിൽ നിന്ന് വ്യത്യസ്തമായിട്ടുള്ള ഒരു ഡൈപോൾ മൊമെന്റ് നമുക്ക് ഒരു പോയിന്റിൽ നമുക്ക് കണ്ടുപിടിക്കാൻ സാധിക്കില്ല. Okay, so this type of stretching vibration, even if it is present in the carbon dioxide, it is not IR active. ഇത് IR active അല്ല, IR inactive. IR inactive അല്ലേ? എന്നാൽ ഇതേ മോളിക്യൂളിന്റെ മറ്റൊരു വൈബ്രേഷൻ നിങ്ങൾ പരിഗണിച്ചു കഴിഞ്ഞാൽ കാർബൺ ഡയോക്സൈഡ്. ഓക്കെ, ആൻഡ് യു ക്യാൻ സീ ദ ബെൻഡിങ് വൈബ്രേഷൻസ്. Bending vibration means after at a certain point of time, the carbon dioxide molecule will be bent like this to some degree. Okay, and after some time it will go here. Okay, it will go here like this. So this is called the bending vibrations. And you can see that in the equilibrium position, the equilibrium position is like this, where the bond angle is 180 degree. Okay, in the equilibrium position, the dipole moment was zero. But if you are checking the dipole moment at this extreme, it is not zero, because the dipole moment of the left carbon oxygen bond is not opposite to the dipole moment of the right carbon bond. Two vectors are not in the exactly opposite direction. Therefore, they will not cancel each other. Okay, so there will be some net dipole moment in this molecule. It means that when this molecule is vibrating in this way, it is accompanied by a change in the dipole moment. So this bending vibration that we can see in the carbon dioxide molecule is IR active. So you know what is the basic requirement for a vibration to be IR active. Okay, IR active vibration means the molecule will be already vibrating in a ground level. For example, ground level, it means V is equal to 0 level. Okay, V is the quantum number here. So it is a level characterized by the quantum number V is equal to 0. And by absorbing radiation, it can excite you another vibration level characterized by the quantum number V is equal to 1. Okay. So when this happens, when this excitement happens, we can say that it is IR active. It is IR active. It is IR active means it can make a transition to an excited state when we can see that it is IR active. And the condition for this IR activity is that the vibration should accompany with a change in the dipole moment. That is the condition. Okay, and you have already seen this or you have already learned this in your previous classes, definitely in the BSc classes. So I am not going to the details of that. You know how the IR radiation interact with the molecule, and that is the reason why there should be a dipole moment change, and all these things you already know. Okay, so let me conclude what I said now. For a molecule to be for a particular vibration to be IR active, that vibration should accompany with a change in the dipole moment. Change in the dipole moment. And here we can depend upon the group theory to predict whether a particular vibration will be IR active or IR inactive. And that is what we are going to do in this class. Identification of the IR active vibrations. We will predict which vibration is going to be IR active and which one is going to be IR inactive. Okay, and that we can do by using group theory. We can obviously do that by using quantum mechanics as well. But the problem is that the steps are lengthier there, and you have to depend upon so much of the computing power. And group theory is actually a shortcut. So group theoretically, very easily you can find out whether a molecule, what are the vibrational modes which is present in a molecule, which are going to be IR active and which are going to be IR inactive. Okay, so that is what we are going to learn in this class. And quantum mechanics already provide with us an equation to predict the spectral transition probabilities. Spectral transition probability means the probability for a spectral transition to occur. Probability for a spectral transition to occur. That is called a spectral transition probability. Let me call the spectral transition probability as P. Okay. And the expression for P is that P is proportional to minus infinity to plus infinity psi I p cap psi f d tau. Sorry, psi I psi f d tau. Okay, psi I psi f d tau. Okay, so this is the expression for the spectral transition probability. Our spectral transition probability is proportional to this one. And I will explain what are these terms involved here in this expression. P cap, here you can see an operator P cap, and this P cap is called the spectral transition or transition moment operator. This is called a transition moment operator. Transition moment operator. Transition moment operator. And this transition moment operator actually depends upon the nature of the spectral transition. There are several reasons for a spectral transitions, right? If you are considering the IR spectroscopy, the spectral transition is from one vibrational level to the another vibrational level, and this is accompanied with a change in the dipole moment, or change in dipole moment can be considered as a pre-requirement for the spectral transition to occur. Okay, so that is the nature of the spectral transition here in the case of IR. But that is not the nature of the spectral transition when we are considering the Raman spectroscopy. There we are considering not the dipole moment, there we are considering the polarizability of the molecule. So different spectral transition will have different natures, and this particular operator will be depending upon the type of spectral transition. Obviously, we are talking about the IR spectroscopy. Therefore, since it is IR spectroscopy, this transition moment operator will be something related to the dipole moment. because it is the dipole moment change which is acting as which is the deciding factor in the IR activity, right? So the transition moment operator will be something related to the dipole moment. And we will go to the details of that in a few minutes. Okay, let me complete explaining the terms involved in this expression. And here I have a term that is psi I. By hearing psi, you can assume that this is a wave function, right? Yes, that's a wave function or it's a state function. And that state function corresponds to the state of the molecule before the transition. Before the transition. Before the transition means the molecule is in the ground vibrational level, right? And whatever may be the wave function corresponding to that, that is psi I. That is the state function corresponding to the initial state. State function for initial state of the molecule. Initial state of the molecule means normally the ground vibrational level of the molecule. And psi f is the state function representing the final state of the molecule. State function for final state. Final state. Final state means after excitation or after the spectral transition. For example, if you are considering this one, the initial state corresponds to V is equal to 0 and the final state corresponds to V is equal to 1 or the excited vibrational state. Okay. So you know psi I and psi f, these are the state functions corresponding to the initial state and final state of the molecule, means the state of the molecule before the spectral transition and after the spectral transition. Okay, and here d tau will be dx if your functions are only of x, d tau will be dy if the functions are only of y. So d tau is a generalized one, right? Generalized. So it can be dx or it can be dy. Sometimes it can be dx, dy, dz, dz if all the x, y, and z are involved here in this expression. You already know this because we have learned this several times in quantum mechanics. Okay. So here we have an expression, and this expression is for the spectral transition probability. And what this equation says, or what this expression says, and this integrand, okay, this integral is actually called the transition moment integral. Transition moment integral. The all integral is called transition moment integral. Transition moment integral. Okay. So this transition moment integral can be sometimes 0. If the transition moment integral is 0, it means that there is no probability for a spectral transition. It means that it is going to be IR inactive. If the transition moment integral has some other value, means a non-zero value, then it means that there is a probability for the spectral transition, right? There is a probability for the transition, or in other words, we can say that that is IR active vibration. Okay. So in order to see whether a particular vibration is IR active or IR inactive, we have to calculate the transition moment integral for that particular mode of vibration. Okay. For example, in water molecule, you have 3 modes of vibration, 3 normal modes of vibrations. These are symmetric stretching, right? Symmetric stretching. Then there is a symmetric bending vibration, and there is anti-symmetric stretching vibration, anti-symmetric stretching vibrations. And we have already assigned the symmetry species corresponding to these normal modes of vibrations. The symmetry species corresponding to the first 2 modes of vibration, that is symmetric stretching and symmetric bending, are A1, right? And the symmetry species corresponding to the last mode of vibration, that is anti-symmetric stretching vibration, that symmetry is a B2 symmetry. And you remember this, we have already done this in the previous class. We assigned the symmetry species for different modes of vibrations present in the molecule, right? And in this class, I am going to tell you which one of these is going to be IR active and which one is going to be not IR active or IR inactive. Okay, and that is what we are going to do. So you already know that in order to find out, we have to get the transition moment integral. And I am now going to talk about this transition moment integral. Okay, and that is a quantum mechanical procedure. We will go with this quantum mechanical procedure first. And whenever we see that this is going to be too much laborious, and then we will try for a shortcut, and that shortcut will come from group theory. That is what we are going to learn today. Okay, so it is very interesting. So let me talk about the transition moment, the probability of a spectral transition and the transition moment operator. And the transition moment operator p cap is nothing but the dipole moment of the molecule, mu. Because the dipole moment of the molecule, which is the deciding factor, dipole moment change of the molecule, which is the deciding factor in our case. Okay, and the dipole moment mu is equal to mu zero plus dou mu by dou q at q is equal to 0 multiplied by q. Okay, I will explain the terms here. Here mu is the dipole moment of the molecule at any instant. Dipole moment at any instant. Dipole moment at any instant. Okay. And mu zero is the dipole moment at the equilibrium position. Dipole moment at the equilibrium position, or you can say this as equilibrium dipole moment. Equilibrium dipole moment. And now what is dou mu by dou q at q is equal to 0? That is the rate of change of dipole moment with the displacement at the equilibrium position. Here q actually represents the general coordinate. Okay, q actually represents the general coordinate. Q can be x if the vibration is only in the x direction. If the vibration is in the y direction, q can be y, and so on. Or if the vibration is in the three-dimensional space, q can be x, y, z, right? Q can have x, y, and z components. Okay, so here dou mu by dou q at q is equal to 0 means that dipole moment change with respect to q, or rate of change of dipole moment with the displacement. Q actually here is the displacement. You already know, we have already learned this in the quantum mechanics about the vibration, right? So it will have displacement from the equilibrium position. If the vibration is in the x direction, you can see that in positive x direction it can come up to plus a, and minus x direction it can come up to minus a, if you are considering this as 0, like that. So here you are actually considering the displacement, right? Displacement. It is the distance from the equilibrium position. So this is the rate of change of the dipole moment with displacement at the equilibrium position. Rate of change of dipole moment with respect to displacement at equilibrium position. That is very important. Okay, so what is the meaning of that? What is the rate of change of dipole moment with respect to displacement at the equilibrium position? See, this is you suppose this one as an oscillator. Okay, this molecule is this point is oscillating between this extreme and this extreme. So equilibrium position is this one. So it is making a displacement to the positive x direction. Okay, and you are considering an infinitesimal displacement dx here. So what is the dipole moment change when this the infinitesimal displacement happens? Okay, that is d mu. Okay, that is d mu. Then d mu by dx is the rate of change of dipole moment with respect to the equilibrium, with respect to displacement at the equilibrium position. We calculated this very close to the equilibrium position. So dx is the displacement from the equilibrium, infinitesimal displacement from the equilibrium position. So that is what you can see here. Dou mu by dou q is the rate of change of dipole moment with respect to displacement at the equilibrium position. And this quantity is multiplied by q, where q is the general coordinate. It can be x, y, or z. Okay, that's the general coordinate. General coordinate. X, y, or z. So here I have given you the transition moment operator, that is nothing but the dipole moment of the molecule. And now you know that the dipole moment mu, it can be resolved into three components. The dipole moment is a vector and it can be resolved into three components along the x-axis, y-axis and z-axis. So what will be the dipole moment component in the x-axis? Dipole moment component in the x-axis. The component of the dipole moment in the x-axis mu x is equal to, from the previous equation, mu 0x plus dou mu by dou q at x is equal to 0. Okay, dou mu by dou, in this case actually it is dou mu by dou x. Okay, dou mu by dou x at x is equal to 0 means that is the equilibrium position multiplied by x. So this is the dipole moment component in the x direction. And similarly you can write the dipole moment component in the y and z directions as well. Okay, you just replace this x with y or z. So since the dipole moment have three components, dipole moment has three components in the x, y and z directions. The probability will also have three components because the spectral transition probability depends upon the dipole moment, p cap in this case is dipole moment. So the spectral transition probability depends upon the dipole moment. Therefore, the spectral transition probability will also have three components in the x, y, and z directions. So let me write the component of the probability P in the x direction. The component of probability P in the x direction can be written as Px. And this Px is proportional to integral minus infinity to plus infinity psi I. In this case, it is mu x, that is the dipole moment component in the x direction. Okay, P cap x is equal to mu x in this case. Then psi f d tau. Okay, psi f d tau. So that is the spectral transitions probability is x component. Probability of spectral transition will have three components, and here I have written the x component. And the total probability of transition. Total probability of transition P will be equal to the component in the x direction plus component in the y direction plus component in the z directions. So you can calculate the components of the probability in the x direction, y direction and z direction, and any of these are non-zero, then you will have a non-zero value for P as well. Okay. So any of the components is non-zero indicate that there is a probability of transition. For example, Px is equal to non-zero. Px is non-zero. But at the same time, Py and Pz can be zero. Okay. In that case also P will have a non-zero value because P is equal to Px plus Py and P0, therefore P will be a non-zero value. It means that there will be a probability of spectral transition. So in order for a spectral transition, or in order for a spectral transition probability to be non-zero, you don't need all the Px, Py and Pz to be non-zero. If any of these are non-zero, then the total probability for transition will be a non-zero value. Okay, and there will be no transition only in the case Px is equal to Py is equal to Ps is equal to 0. If all the components are 0, then the total transition probability P will also be 0. In this case, it will be inactive, or there will be no spectral transition. So in this case, it is IR active, and in this case, it is IR inactive. IR inactive. Okay. So this is what we can understand from here. And now I am going to expand this expression for Px. We have an expression for Px which is proportional to minus infinity to plus infinity psi I mu x psi f d tau. What I am going to do is I am going to give the expression for mu x here. Okay, I am going to give the expression for mu x here. I am going to substitute with the mu x there. Okay. And when I am substituting for mu x in this equation, Px is proportional to minus infinity to plus infinity psi I. What is the expression for mu x? Mu x is equal to mu 0 x plus dou mu by dou x at x is equal to 0, okay, multiplied by x. Then what is remaining? Psi f theta. Okay. So that is equal to, so this expression is equal to minus infinity to plus infinity. So let me take this one, mu 0 x. Mu 0 x is the dipole moment at the equilibrium position. The equilibrium position has no change, right? Equilibrium position is a fixed position. So this dipole moment corresponding to the equilibrium position will have a constant value. So you can consider mu 0 x as a constant. So let me write it like mu 0 x, that is a constant, minus infinity to plus infinity psi I psi f d tau plus, now what is next? Dou mu by dou x at x is equal to 0. It means the change in the dipole moment at the equilibrium position. This is the change in dipole moment at a particular specified position. Specified position in this case is the equilibrium position. Equilibrium positionilulla dipole moment change, that is also a constant value, because equilibrium position is a fixed one, and we are going to say the dipole moment change with respect to displacement at the equilibrium position. Okay, so that is also a fixed value. So let me take this one also out of the integral sign. So I can write it like dou mu by dou x at x is equal to 0, then integral psi I, then x is there, that is not fixed, that is the displacement, it can vary, right? So psi I x psi f d tau. Okay, that's my expression. And here you have to see that psi I and psi f are the wave functions for the initial and final state of the system. The wave function for the initial and final state of the system. This is a wave function of the same system, but these wave functions are representing different states. And the wave function of the same system representing the different states will be orthogonal to each other. This one you already know from the quantum mechanics. So psi I and psi f are the orthonormal functions. They are normalized, at the same time they are orthogonal to each other. Therefore, integral psi I psi f d tau will be equal to 0. Okay, this will be equal to 0. This is equal to 0. Integral psi I psi f d tau is equal to integral minus infinity to plus infinity integral psi I psi f d tau is equal to 0. Therefore, the first term will vanish from this expression. Then what is remaining? Only the second term will remain. Means Px is proportional to this one. This is a constant. Then integral minus infinity to plus infinity psi I x psi f d tau. Okay, so let me write it here. Integral Px, Px is proportional to dou mu by dou q, dou mu by dou q, okay, or dou x at x is equal to 0, at x is equal to 0, integral minus infinity to plus infinity, okay, psi I x psi f d tau, okay. And now you know that this is a constant, right? This is a constant. This one is a constant. So when we have the proportionality sign, we don't need to keep the constant here. Even if we are removing the constant here, the proportionality sign will remain like that, right? So we can simply avoid this constant. So I can write it like Px is proportional to integral minus infinity to plus infinity psi I x psi f d tau. Okay, psi I x psi f d tau. And now we know that now we have a simpler expression for the transition moment integral, right? And this is a component of the probability in the x direction, and this is a simpler expression because we have a simple term in place of the operator, the transition moment operator, that is nothing but the x coordinate. Okay, and if this integral is 0, then it means that if it is equal to 0, no transition, it means it is IR inactive. And if this integral is non-zero, it means that there will be a probability for transition. It means that it will be IR active. Okay, this is what we can understand from here. So in order for a transition to be IR active, a component like this should be non-zero. You don't need Px to be non-zero. Like Px, it can be Py or Pz. For example, Px can be written like Py can be written like Py is proportional to minus infinity to plus infinity psi I y psi f d tau, and Pz is proportional to minus infinity to plus infinity psi I z psi f d tau. Okay. If any of these probabilities are going to be, or any of these probabilities are emerging to be non-zero, then there is a probability for the spectral transition, or the transition will be IR active. Okay. And now I am going to utilize these equations for predicting whether a particular mode will be IR active or IR inactive. I am going to take the case of the water molecule itself, because we have already assigned the symmetry species for different vibrational modes in water molecule. Okay, and I am going to assign whether these are going to be zero, whether these are going to be non-zero. How you can do this? Okay, these are in the equations, the integrations, and psi I and psi f will have some complex form, right? Complex means complex form. By saying complex form means I said it will have some complicated expressions. Okay, and it can be real or imaginary, and we have to do this in the integration. And when the psi f and psi I and psi f are very complicated expressions, then the integrations are going to be very lengthy. Most of the time you have to depend upon a computer for doing this calculation. And at the end, the computer will tell you whether these integrals will 0 or non-zero. The computer will give you the exact value for these integrals. And actually, we don't need the exact values for this integral, right? We only need to know whether these integrals are going to be 0 or non-zero. We are not interested in the exact value. Okay, exact value is interesting, of course. But in order to predict whether a particular vibration is IR active or not, we don't need the exact value of this integral. We need only to know whether this integral is 0 or non-zero. Of course, computer can say that. But group theory can also say that. What is the difference of the computer and group theory? In computer, you have to depend upon the computing power. You have to depend upon the psi functions, the wave functions. You must have some understanding about these wave functions, right? And there should be some program to calculate these wave functions. And that is going to be a tedious process. But why do you want to depend upon such tedious process when you can do it just by looking at the character table? That is easier. So group theory makes this easy. The group theory will tell you whether these integrals are going to be 0 or non-zero. Okay, that is what we are going to do. For that, we have to know the symmetry of each of these expressions. By saying that, I am going to say that I want to say the symmetry of psi I, symmetry of the initial vibrational state, symmetry of the final vibrational state, and symmetry of the operator. If you know these things, the symmetries of all the terms involved here, then you can predict whether this integral is going to be 0 or non-zero. Okay, and now you may be remembering the class that I took for direct products. Direct products. There I had given an indication of this one. Okay, don't fear. I am going to explain that in detail. Okay, in a very easy way. So we need to get the actual symmetry of the modes involved here, or actual symmetry of the vibrational states involved here. That is what we are going to do now. It is very easy. Now, how to get the symmetry of the various vibrational levels? You already know the symmetry of the normal modes. For example, if you are taking the water molecule, the symmetry of the vibrational modes are 2A1 plus B2, right? Means two of the vibrations are of A1 symmetry and one vibration is of B2 symmetry. And these are the symmetries of these normal modes. And these 2A1, they stands for symmetric stretching and symmetric bending. And the B2 stands for the anti-symmetric stretching. And you know that during an IR transition, there will be a transition of the molecule from V is equal to 0 to V is equal to 1 state, right? V is equal to 0 to 1, V is equal to 1 state. This is called the fundamental transition. Fundamental transition. Fundamental transition. Fundamental transition. Okay. So now we need to know the symmetries corresponding to each vibrational state of a normal mode. These are the symmetry species of normal modes of vibration. What are the normal modes of vibrations? The symmetric stretching, then symmetric bending, and then anti-symmetric stretching. Okay, these are the normal modes of vibrations. We know the symmetry corresponding to these normal modes of vibrations. And now how we are going to assign the symmetry corresponding to each vibrational state for these normal modes of vibration. For example, the molecule which is executing a symmetric stretching vibration can sit in the V is equal to 0 state. And by absorbing the radiation, the molecule which is executing the symmetric stretching can excite to the V is equal to 1 state. So in both of this state, this molecule is executing the symmetric stretching vibration. So is the case with the symmetric bending and anti-symmetric stretching. So within each normal mode of vibration, the molecule can sit in different vibrational levels, right? Within each normal mode of vibration, like symmetric stretching, the molecule can sit in the different vibrational levels. Within the symmetric bending mode, the molecule can sit in the different vibration levels like V is equal to 0, V is equal to 1, etc. And so is the case with anti-symmetric stretching. So when you are considering the spectral transition, it is actually not a transition from symmetric stretching to symmetric bending or symmetric bending to anti-symmetric stretching. It is not like that. Within a particular mode, it is making transition from one vibration level to the next vibrational level. Okay, that is actually what is happening. നിങ്ങൾ സ്പെക്ട്രോസ്കോപ്പി പഠിക്കുമ്പോൾ ഇത് വിശദമായിട്ട് പഠിക്കും. അതായത് സിമെട്രിക് സ്ട്രെച്ചിങ് നടത്തുന്ന ഒരു മോളിക്യൂളിന് അതിൻ്റെ ഗ്രൗണ്ട് വൈബ്രേഷൻ ലെവലിലിരിക്കാം. അതേ സിമെട്രിക് സ്ട്രെച്ചിങ് മറ്റൊരു ഹയർ വൈബ്രേഷൻ ലെവലിൽ ഇരുന്നുകൊണ്ട് നടത്താം. എന്തായിരിക്കും വ്യത്യാസം? വ്യത്യാസം എന്ന് പറയുന്ന ആംപ്ലിറ്റ്യൂഡിലാണ് വ്യത്യാസം. വൈബ്രേഷൻ്റെ ആംപ്ലിറ്റ്യൂഡിലാണ് വ്യത്യാസം. ഓക്കെ, അപ്പോൾ ഓരോ വൈബ്രേഷനും പല ഗ്രൗണ്ട് വൈബ്രേഷൻ ലെവലിൽ ഇരുന്നുകൊണ്ട് നടത്താം. So now you know the symmetries corresponding to these. Symmetric stretching has A1 symmetry. Symmetric bending has A1 symmetry. Anti-symmetric stretching has B2 symmetry. This one you already know. We already did this in the previous class. Now you have to assign the symmetries corresponding to each of these vibrational levels. So how you will do that? It is very easy. Okay. For symmetric stretching, when the molecule is the ground vibrational level, the symmetry corresponding to that is A1 raised to 0. Actually, the general form is A1 raised to V, where V is equal to 0 here. That is equal to A1. And when it is exciting to the V is equal to 1 state, then its symmetry species is A1 raised to 1. A1 raised to 1 is also equal to A1. So why A1 raised to 0 is equal to 1? Because anything raised to 0 is equal to 1. So it will be 1, 1, 1, 1, right, in the character table. So it is A1 symmetry. Anything raised to 1 is the same. A1 is already 1, 1, 1, 1. So A1 raised to 1 is also equal to A1. And symmetric bending, this one also is A1 raised to 0 for ground vibration level, that is equal to A1. And A1 raised to 1 for excited vibration level, that is also equal to A1. And in the case of anti-symmetric stretching, the ground vibrational level has the symmetry B2 raised to 0. That is equal to A1. Why B2 raised to 0 is equal to A1? You can look at the character table. What is B2? B2 is 1 minus 1, 1 minus 1, 1. And B2 raised to 0 means you have to take 1 raised to 0, minus 1 raised to 0, minus 1 raised to 0, 1 raised to 0. Any number raised to 0 is equal to 1. That is why it is B2 raised to 0 is 1, 1, 1, 1, right? So B2 raised to 0 is equal to 1, 1, 1, 1, and 1, 1, 1, 1 corresponds to A1 symmetry, right? That is what written here. B2 raised to 0 is equal to A1 symmetry. It means that the ground vibrational level in the anti-symmetric stretching also has the A1 symmetry. Okay. What about the final vibration level, or V is equal to 1? B2 raised to 1. That is the excited state. There it is equal to B2. So what are the spectral transitions? Within the symmetric stretching, the spectral transition is A1 to A1. Means ground vibration to excited vibration is A1 to A1 within the symmetric stretching vibrational mode. When we are considering the symmetric bending vibrational mode, the vibrational transition is also A1 to A1. And when we are considering the anti-symmetric stretching, the vibrational transition is from A1 to B2 symmetry. Okay, A1 to B2 symmetry. So here you can see three different modes of vibrations, and corresponding to three modes of vibrations, there will be three types of spectral transitions. And the first one corresponds to an A1 to A1 transition. The second one is A1 to A1 transition. And the third one is A1 to B2 transition. And here you have to consider that all the ground vibration levels are of A1 symmetry. Okay, because anything rise to 0 is equal to 1. All the ground vibration levels are totally symmetric. A1 is totally symmetric. So all ground vibration levels are totally symmetric. That is psi I in all the case. Psi I in all the case is equal to A1. This is psi I, A1, A1, A1. And now this is psi 2. Psi 2 has the symmetry A1, A1 and B2 for the three vibration modes. So psi 1 has the symmetry A1 in all cases. But the psi 2 can be A1, A1 or B2. Okay. For the first two means symmetric stretching and symmetric bending, it is A1. And for the last one, that is anti-symmetric stretching, it is the B2. The final state is B2. So now you know how to assign the symmetry of the various vibrational levels or symmetry corresponding to psi I and psi f. You already know. This is very easy. Look at the character table. You can assign the symmetry corresponding to various vibrational levels. Now what is the symmetry corresponding to the operator? And operator in our case is x if we are going to calculate px, right? Operator is x in this case. In the case of px, operator is x, and in the case of py, it is y, and so on, right? So we have to get the symmetry species corresponding to x also. That is also very easy. You look at the character table and see how x transforms. You can see in the third area of the character table x, y, and z. And here you can see the x, and x transforms as B1 symmetry. X transforms according to B1 symmetry. So you can assign the symmetry of the operator also here, right? Symmetry of the operator. And x corresponds to B1 symmetry. Now you know in the transition moment integral, what are the symmetry species corresponding to each term, psi I, x, and psi f, for different modes of vibrations. Okay, and what I am going to do now, I am going to do these calculations for the symmetric stretching and the bending modes. Symmetric stretching and bending modes. For symmetric stretching and bending modes. Symmetric stretching and bending. Symmetric stretching and bending modes. Let me calculate the px for symmetric stretching and bending modes. Px is proportional to minus infinity to plus infinity psi I x psi f d tau, right? Psi I x psi f d tau. And we want to know whether this integral is 0 or non-zero. That's all. How can we know? I am going to take the direct product of the symmetry, the irreducible representations corresponding to this. Okay. So the psi I, in all the cases, psi I is equal to is of A1 symmetry. And x, in this case, x transforms as B1. We already said this, right? X transforms as B1 symmetry. So x is B1. X is of B1 symmetry. And psi f is of A1 symmetry in this case, right? Psi f is of A1 symmetry. Because in the case of symmetric stretching and symmetric bending, the excited vibration has A1 symmetry. Okay, so psi f is A1 symmetry. So A1 B1 A1, that is equal to A1 B1 A1 is equal to B1. And B1 is not totally symmetric. It is not totally symmetric. Totally symmetric. And now this is an important observation or important result. This integral will be 0. This integral will be 0 if the direct products of A1, B1 and A1 gives you a representation which is not totally symmetric. നമ്മൾ ഡയറക്റ്റ് പ്രൊഡക്റ്റ് മെട്രീസസിൽ പഠിച്ചതാണ്, ഡയറക്റ്റ് പ്രൊഡക്റ്റ് റെപ്രസെൻറ്റേഷൻസിനകത്ത് പഠിച്ചതാണ് അല്ലേ? So if you are taking the direct products of A1, B1 and A1, if the result is a if not totally symmetric representation, if the resultant representation is not totally symmetric, then the integral will be 0. The integral will be 0. Therefore, Px in this case will be 0. So Px is equal to 0. So how can you know whether Px is equal to 0? You just assign the symmetry of these products, direct products of the representations corresponding to these. That is A1, B1. A1 is equal to B1, which is not totally symmetric. Only one totally symmetric representation is there, that is A1. Okay. Since it is B1, Px is equal to 0. So Px is a 0. And now what about Py? Py. And we know that from the character table, y transforms as B2, right? Y transforms as B2. So that is very important for us. Y transforms as B2. So y corresponds to B2 symmetry. Y corresponds to B2 symmetry. So what is the transition moment integral? Okay, in this case, or the probability of the transition, the component of probability of transition in the y direction, Py, is proportional to minus infinity to plus infinity psi I, y, in this case it is y, psi f d2. That is equal to integral minus infinity to plus infinity psi I, in this case is a1. Okay. And psi f is also a1 for symmetric stretching and bending modes. But what about y? Y transforms as b2. Okay. So let me write psi 1. Okay. You don't need to write integral there. Sorry. You don't need to write integral there. So we have to assign this one. So how to assign this one? Psi I is equal to a1. Okay. Then y is b2. And again psi f is a1. a1 b2 a1 is equal to b2. That is not totally symmetric. This is not totally symmetric. Therefore py is also equal to 0. Py is also equal to 0. Now we have to check pz, right? Pz. So let me check pz. And pz is equal to integral minus infinity to plus infinity. It is actually proportional to infinity minus infinity to plus infinity. Psi I z psi f d2. And now we have to know how z transforms. And group theory says that z transforms as A1 species, right? So z corresponds to A1 species. So what about this integral, whether it is 0 or non-zero, that we can get from the direct products? Psi I corresponds to A1, z corresponds to A1, and psi f also corresponds to A1 for symmetric stretching and bending. So A1 is equal to A1, which is totally symmetric. Totally symmetric. So this direct product gives you a totally symmetric representation. Therefore, the integral corresponding to that will be a non-zero integral. Therefore, it means that Pz is not equal to 0. Okay. And you know that the total probability P is equal to Px plus Py plus Pz. Px and Py are equal to 0, but Pz is not equal to 0. Therefore, P is also not equal to 0. It means that the symmetric stretching and bending modes are IR active. But this probability is a non-zero value. We consider modes IR active. Symmetric stretching carry out in a molecule and a ground vibrational level excited vibration level. Like that, a molecule which carry out the symmetric bending can go from the ground vibration level to the excited vibration level by absorbing radiation. Okay, so that both of these vibrational modes are IR active. So symmetric stretching and symmetric bending, okay, symmetric bending are They are IR active. They are IR active. That is the result we can get from the grip theory. So you don't need to solve this complicated integral by using a computer. You can get whether the integral is having a non-zero or zero value by looking at the symmetry, okay, or by looking at the character table. So symmetric stretching and symmetric bending are IR active. Now I am going for the anti-symmetric stretching. Anti-symmetric stretching, that is the last mode of vibration. Anti-symmetric stretching, right? Anti-symmetric stretching. The last mode of vibration. Anti-symmetric stretching. Anti-symmetric stretching. And for that I am going to calculate the Px, Py and Pz. So Px is proportional to minus infinity to plus infinity. Psi I, x psi f d2. What about the psi I and psi f in this case? In the case of anti-symmetric stretching, psi I is A1, right? This is II. And psi f is equal to B2. So the ground vibration level corresponds to A1 symmetry. Excited vibration level corresponds to B2 symmetry. So actually it is a transition from the A1 symmetry to B2 symmetry. So psi I is equal to A1. Psi I is of A1 symmetry and psi f is of B2 symmetry. So when we are assigning the symmetry, we have to take care of that. Okay, it is not A1 A1, it is A1 B2. And now we have to look at the character table and see how X transforms. X transforms as B1. X transforms as B1. So we already know X transforms as B1 symmetry, transforms according to B1 symmetry. Therefore, whether this integral is 0 or non-zero, we can depend upon the direct products. Okay, the direct products of the terms involved here. That is, the symmetry of psi I is A1. Ground vibration level is always A1. And symmetry of X is B1. And the symmetry psi F is equal to B2. And that is A1 B1 B2. A1 B1 B2. And A1 B1 B2. What about A1 B1 B2? You look at the character table. A1 B1 B2. Okay, 1 1 1, that is equal to 1. Then 1 minus 1 minus 1, that is also 1. Then 1 1 minus 1, that is equal to minus 1. 1 1 1, that is equal to 1 1 1, that is equal to 1, right? So we have, let me write it here with another color. A1 B1 B2, A1 B1 B2, that is equal to 1 1 1, that is equal to 1. Okay, 1. Then 1 minus 1 minus 1, that is 1. Then 1 1 minus 1, that is equal to minus 1. Okay, and 1, then 1, then 1, that is equal to 1. Okay, there is some error here. I have to find out where is that. 1 1 1 1 1 1 minus 1 minus 1. Okay, here it is. So this is minus 1. Okay, the character table, you have to see that this is minus 1. This is minus 1. Okay, B1 is a minus 1. So 1 minus 1 1, that is equal to minus 1. This is minus 1. So we have 1 1 minus 1 minus 1. Okay, 1 1 minus 1 minus 1. So 1 1, what is 1 1 minus 1 minus 1? 1 1 minus 1 is this one. 1 1 minus 1 minus 1. So that is A2 symmetry. So this one is of A2 symmetry. So when we are taking the product of that, it is A2 symmetry. So let me write it there as A2. So this is A2. And A2 is not totally symmetric, right? Not totally symmetric. Since it is not totally symmetric, Px will be equal to 0. Px is equal to 0. And now what about Py? Py is proportional to minus infinity to plus infinity. Psi I y psi f d2. Okay, and you know that y transforms as b2 from the character table. Y transforms as b2. You know this, right? Y transforms as b2. So y transforms as b2. Therefore, what about the direct product of these the representations? Psi I is a1, y is b2, psi f is also b2. So a1 b2 b2. What is a1 b2 b2? That is equal to a1. Okay. So you already saw in the when we were talking about the direct products, we saw that b2 b2 will be always equal to the totally symmetric a1. Okay, so if two of these are coming together, then the direct product of these two will be a totally symmetric representation, and a1 is equal to a1. Okay, so it is a1. So in this case, py will be non-zero. Py is non-zero. This is because it gives the direct product gives a totally symmetric representation. Therefore, I can write py is not equal to 0. And what about Pz? Pz is proportional to minus infinity to plus infinity psi I z psi f d2. Okay. And what are the symmetries corresponding to that? Z transforms as a1, right? Z transforms as a1. Z transforms as a1. So the symmetry, the direct products of these are psi I a1 and z a1 and psi f b2, that is equal to b2. Okay, that is not totally symmetric. It means that pz is not equal to pz is equal to 0. So pz is equal to 0. Pz is equal to 0 because it is not totally symmetric. And in this case, px is equal to 0, pz is equal to 0, but py is not equal to 0. Therefore, the total probability P is equal to Px plus Py plus Pz, which is not equal to 0 because one of these components is non-zero. So the total probability is a non-zero value. It means that this one is IR active. IR active. So anti-symmetric stretching is also IR active. It means that it can go from its ground vibration level to the next higher vibration level by absorbing the IR radiation. So anti-symmetric stretching is IR active. So far we have seen that the three modes of vibration, so symmetric stretching, symmetric bending, and the anti-symmetric stretching, all three modes of vibrations in water molecule are IR active. Okay, we didn't solve any integration or we didn't go for any details of any integration. We didn't depend upon a computer. Just by looking at the character table, we assigned whether a particular vibration is going to be IR active or IR inactive. Okay, so that is a very beautiful piece of information that we can get from group theory very easily. Okay, so what you will understand from here? How can we assign, how can we see whether a particular vibration is going to be IR active or not just by looking at the character table? See the previous case, whether when we checked the symmetric stretching and symmetric stretching and bending. In that case, Pz was a non-zero value. Px and Py were 0. Px and Py were 0, but Pz was non-zero. Pz was non-zero, right? And now you look at the character table. In the case of Pz, Z is the transformation vector. Okay, not a transformation vector, transition, the transition moment vector. Okay, so transition moment operator. Sorry, not vector. Transition moment operator. So the transition moment operator in this particular case, actually it is not the transition moment operator. The operator in place of the transition moment operator is Z. Okay, so in the case of Pz, it is a Z coordinate, simply the Z coordinate which is a vector, which is the operator here. And now you look at this character table, Z. Z belongs to A1 symmetry. Okay, and this A1 symmetry is the final state of the vibration also. You know that in the ground state always is A1. A1 is totally symmetric. So in the integrals, this is not going to determine whether it is going to be totally symmetric or not totally symmetric. What are the determining factors? X and psi f, or y and psi f, or z and psi f, because psi I will be always A1. Okay, that is not a determining factor. But their symmetry, the symmetry of these two, will be important. That is actually going to determine whether the direct product will be totally symmetric or not totally symmetric. Okay, if x and psi f has the same symmetry, then the product will be A1. Okay, x and psi f has the same symmetry, then the product will be A1. Okay, so when you are calculating for x, you have to see whether the final state has the same symmetry of the x in the character table. And you can see here that in the character table, the final state for the first two modes of vibration is A1. And you look whether any of the Cartesian coordinates are belonging to this. Okay, here you can see that the z, okay, z belong to A1 symmetry, the final vibrational state. So any of these Cartesian coordinates are belonging to the final vibrational state, the symmetry of the final vibrational state. Then the integral corresponding to that will be a non-zero. It will be a totally symmetric representation. Okay, the integral corresponding to that will be totally symmetric, or that integral will be non-zero. So we have z here in place of A1. So we can see that those vibrational modes for which A1 is the excited mode will be IR active. These are stretching mode, symmetric stretching and symmetric bending. Symmetric stretching and symmetric bending in the case A1 എന്ന് പറയുന്നതായിരുന്നു അതിന്റെ excited state എന്ന് പറയുന്നതിന്റെ symmetry. ആ A1 ൽ തന്നെയാണ് Z വരുന്നത്. അതുകൊണ്ട് അത് എന്തായിരിക്കും? അങ്ങനെ എക്സൈറ്റഡ് സ്റ്റേറ്റ് വരുന്ന മോഡുകളെല്ലാം എന്തായിരിക്കും? അല്ലെങ്കിൽ psi f വരുന്ന മോഡുകളെല്ലാം IR ആക്റ്റീവ് ആയിരിക്കും. എന്നാൽ രണ്ടാമത്തേത് അതിനകത്ത് സിമെട്രിക് ആന്റി സിമെട്രിക് സ്ട്രെച്ചിങ്, അവിടുത്തെ psi f ന് B2 സിമെട്രി ആയിരുന്നു. അപ്പോൾ നമ്മൾ നോക്കുക, B2 സിമെട്രിയിൽ ഏതെങ്കിലും കാർട്ടീഷ്യൻ കോർഡിനേറ്റ്സ് വരുന്നുണ്ടോ? യെസ്, y is there. Therefore the transition moment integral corresponding to y, that will be totally symmetric or it will be non-zero value. അതാണ് നമ്മൾ അവസാനം ചെയ്തല്ലേ. നമ്മൾ കണ്ടു py എന്ന് പറയുന്നത്, py was a non-zero value. py had a non-zero value. This is because in this case the psi f has B2 symmetry. In the same B2 symmetry itself y is also coming. Therefore py will be non-zero. അപ്പോൾ ഒരു പർട്ടിക്കുലർ വൈബ്രേഷൻ IR ആക്റ്റീവ് ആണോ IR ഇനാക്റ്റീവ് ആണോ നോക്കണമെങ്കിൽ നിങ്ങൾ എന്ത് ചെയ്താൽ മതി? You look what is the excited state of that vibrational mode. Okay, excited state means V is equal to one state. We are looking at the fundamental vibration. Okay, fundamental transition. അപ്പോൾ excited state എന്ന് പറയുന്നത് V is equal to 1 ആണ്. V is equal to 1 ആകുമ്പോൾ നോർമൽ മോഡ് റൈസ് ടു 1 ആണ്. അതായത് നോർമൽ മോഡ് തന്നെ. A1ഉം B2ഉം ആണ് നമ്മുടെ നോർമൽ മോഡ്സ്. ആ നോർമൽ മോഡ്സിൽ ഏതെങ്കിലും കാർട്ടീഷ്യൻ കോർഡിനേറ്റ്സ് വരുന്നുണ്ടോ എന്ന് നോക്കിയാൽ മതി. So you get the vibrational, you get the symmetries corresponding to the normal modes of vibrations and look whether any of the Cartesian coordinates are coming in the same symmetry. Okay, if that is the case, then these vibrations will be IR active. നമുക്കറിയാം നമ്മളുടെ സിമെട്രിക് സ്ട്രെച്ചിൻ്റെയും സിമെട്രിക് ബെൻഡിൻ്റെയും മോഡ് ഓഫ് വൈബ്രേഷൻ A1 ആയിരുന്നു. അതുകൊണ്ട് Z അവിടെ വരുന്നുണ്ട്. അതുകൊണ്ട് ആ രണ്ട് മോഡ്സും IR ആക്റ്റീവ് ആണ്. നമ്മുടെ സിമെട്രിക് ആൻറ്റി സിമെട്രിക് സ്ട്രെച്ചിങ്ങിൻ്റെ മോഡ് ഓഫ് വൈബ്രേഷൻ B2 ആയിരുന്നു. അതിനകത്ത് Y വരുന്നുണ്ട്. അതുകൊണ്ട് അതും IR ആക്റ്റീവ് ആണ്. So that is the conclusion here, right? So just by looking at the character table you can predict. We don't need to do any of these things. Just by looking you can see. Okay, so if the normal modes belong to the same representation as any one of the several of the Cartesian coordinates, then it will be IR active. That is our conclusion. So let me write it here. A fundamental mode will be IR active. This is very important. A fundamental mode will be IR active. A fundamental mode, fundamental mode will be IR active, if the normal mode belongs to, belongs to the same representation, as any one or several of the Cartesian coordinates. Cartesian coordinates x, y, z. Okay. അപ്പോൾ എക്സ് വൈ ഇസഡ് ഇതിൽ ഏതെങ്കിലുമോ അല്ലെങ്കിൽ അതിൽ ഒന്നിലധികമോ രണ്ടോ മൂന്നോ ഇത്രയായാലും നമ്മുടെ നോർമൽ മോഡ്സ് ഓഫ് വൈബ്രേഷൻ്റെ അതേ സിമെട്രി സ്പീഷീസിലാണ് വരുന്നതെന്നുണ്ടെങ്കിൽ അത് IR ആക്റ്റീവ് ആയിരിക്കും. ഓക്കെ, വെരി ഈസി, റൈറ്റ്? സോ ദിസ് ഈസ് ഹൗ യു ക്യാൻ ഐഡൻറ്റിഫൈ the IR active vibrations using group theory. In C2B point group, any mode belonging to A2 symmetry will be IR inactive. വാട്ടർ മോളിക്യൂളിൻ്റെ കേസിൽ അങ്ങനെ ഒരു ഒരെണ്ണം ഇല്ലാമായിരുന്നു. വാട്ടർ മോളിക്യൂളിൻ്റെ കേസിൽ 3 മോഡ്സേ ഉള്ളൂ. അത് A1 ഉം 2 A1 ഉം ഒരു B2 ആയിരുന്നു, അല്ലേ? എന്നാൽ നമ്മൾ ഏതെങ്കിലും ഒരു മോളിക്യൂളിൻ്റെ കേസിൽ A2 എന്ന് പറയുന്ന ഒരു സ്പീഷീസ് കാണുന്നത് തന്നെ ഇരിക്കുക. ഇതേ പോയിന്റ് ഗ്രൂപ്പിൽ വരുന്ന C2B പോയിന്റ് ഗ്രൂപ്പിൽ വരുന്ന ഏതെങ്കിലും ഒരു മോളിക്യൂളിൻ്റെ കേസിൽ you see that A2 is also a vibrational, A2 also corresponds to some mode of vibration. അങ്ങനെ നിങ്ങൾ കണ്ടു കഴിഞ്ഞാൽ ആ A2 എന്ന് പറയുന്ന മോഡ് ഓഫ് വൈബ്രേഷൻ എന്ന് പറയുന്നത് അത് IR ആക്റ്റീവ് ആയിരിക്കില്ല. കാരണം എന്താ? ഈ A2 മോഡിൽ നമുക്ക് എക്സോ വൈയോ ഇസഡോ ഒന്നുമില്ല. നമുക്ക് ബാക്കി എല്ലാ മോഡ്സിലും ഉണ്ട്. A1-ലുണ്ട്, B1-ലുണ്ട്, B2-ലുണ്ട് എക്സ് വൈ ഇസഡ്, അല്ലേ? പക്ഷേ A2-ൽ നോക്കി കഴിഞ്ഞാൽ നമുക്ക് എക്സോ വൈയോ ഇസഡോ അവിടെ ഇല്ല. Therefore, if you find any vibrational mode which belongs to the A2 symmetry in the C2B point group, in that case, that vibrational mode will be definitely IR inactive, because you cannot find any of the Cartesian coordinates having the same symmetry. Okay, so this is very important, and I hope that you understood completely how we can depend on the group theory to assign whether a particular mode of vibration will be IR active or IR inactive. Hope you understood this one. If you have any doubt, please don't hesitate to ask me. Thank you for watching and stay tuned.